first. Here we go. All right, so we are recording. Um, Today's lecture is going to be centered around this particular module. Okay, it has to do with algorithms to search for an item in an array. In other words, if I give you an array of, let's just say numbers, okay, integers, how can you confirm, one way or another whether a particular integer or value is in the array or not? That's all I need to know, okay, is whether it is in the array or not. So the purpose of talking about these algorithms is, on one hand, it is about just reinforcing what we know about arrays because it does use arrays, and also the concept of nested control structures. In other words, we have loops, and then we have conditional statements, and then we have conditional statements inside of a loop in some cases, and in the other one it's really simple. Well, or it seems to be simple, okay, but it still makes use of the lazy evaluation of Boolean expressions, or the short-circuited way of evaluating Boolean expressions. So a lot of the stuff that we talked about in the previous module, which is only on arrays, is going to be kind of recurring here. Okay, this is a reinforcement. But the other purpose of talking about these algorithms is binary search, okay, which is its own kind of bigger topic in this particular module, is also a very interesting algorithm, this one over here. So when you look at the code, it is a little bit more complex compared to the other search algorithm, the linear search method. But the binary search method is exceptionally efficient. In other words, the number of times you have to compare in order to confirm whether a particular value is in the array or not is really small, okay, compared to potentially how many things are in the array. So it basically opens up the discussion of a way of looking at a problem, or a way of how to solve a problem, but in a very, I would say at this level, okay, I would say it's a very ingenious way of solving that problem. So those are the rationale behind this particular module of why we have to look into these algorithms or methods of doing things. Without any you know explanation, 0054 is probably the module that talks about arrays, because we do need to understand arrays before we can talk about sorted arrays. So sorted array means, in the array, the items are in the sorted order, which basically means it's either in a non-increasing order, which implies you can have the same value over repeating a few times, or it is in a non-decreasing order. So in this class, unless we say anything otherwise, we're going to be using the non-decreasing order, ordering, which means, the first item of an array A is going to have a value that is less than or equal to the second item, which is less than or equal to the third item, and so on. So the last item, assuming n represents the number of items in the array, would be the largest one. Okay, so if you want to look for the maximum of the values in an array when the array is sorted in a non-decreasing order, all you have to do is to go to the last item, because that is guaranteed to have the largest value. Is all, all of this making sense so far? Yep. It means it can be 0, 0, 1, 1, 2, 2, 3, 4, 5, 6, 1,000. That is non-decreasing because they can still be the same. Sorry? So if it is decreasing, that would be 5, 4, 3, 2, 1. That would be decreasing. But 5, 5, 4, 4, 3, 2, 1 is not decreasing because two items can have the same value, so they're not decreasing because they can be the same. So the nuance is, this is a less than or equal to instead of just less than. Yep. So you can have two values of the same in the array. So that makes it non-decreasing instead of increasing. Yep. So that's a very good point. Okay, I'm glad you asked that question because to many people, it would seem like I'm just making things unnecessarily confusing, but it is not. Okay, because there is a very important, even though it may not be obvious, there's an important difference between non-decreasing versus increasing. Because in the case of a non-decreasing order, you can have items of exactly the same values, but not when it is increasing. So the implications are different. All right. Any other questions about what these terms mean? In other words, what is sorted, what is non-decreasing, what is increasing, and also the syntax that we are using here to describe what is non-decreasing. Not on the test on Wednesday. This entire module will not be in the scope. Yep. Even the race would not be in the scope. Hmm? Oh, okay. Well, you know where to find the recording, right? Yes. The link is in the Canvas shell. So use that so that you can actually rewatch the videos if you need to. And you can watch it as many times as you want. All right. So, shall we proceed to talk about this? Okay. So the first algorithm is not even to ask whether an item is in the array or not. This one is only going to determine whether the array is even sorted or not. Okay, because if you want to apply um, the binary search algorithm, you actually need to make sure the array itself is already sorted. Okay, so you look at this and go like, well, this is a very simple algorithm. It only has 6 lines and it's not even searching for anything in the array. So it doesn't look like it is very interesting. Well, I mean, just look at it line by line and it will see whether it is interesting or not. Line one, yeah, that's pretty boring stuff. Okay, it's a variable. The right hand side is a value of 0. We just change the left hand side, which is variable I to 0. Okay, easy peasy. The second line looks a little bit interesting already. It's like, are we, can we do something like this? In other words, it is still an assignment operation, an assignment statement if you include the semicolon. The right-hand side does not specify integer anymore. It is specifying a Boolean value. Okay, so true, false are Boolean values because there are only two choices here. Okay, it's either true or false. C++ has the concept of a Boolean value as opposed to an integer value. C, which is the basis of C++, does not. Okay, but since you guys are all graduating to CISP 360, where they mostly focus on C++ and so much on C, which is kind of a slightly more primitive programming language, I think it is good to understand that you can have Boolean expressions and Boolean values. So true is really just a Boolean value. Okay, it is of a different type compared to integers, but nonetheless, it is just specifying a value. So the other side is sorted, which is a variable. Okay, it is a variable that can store different values. Okay, one at a time. Okay, but in this case, we're just going to change the value of sorted to be true. Okay, so when we trace this, it'll be kind of obvious, that oh, okay, so it's not any really much different compared to what we already have seen. And we also use n in this case to represent the number of elements in the array because we kind of need that in order to determine are we done? Because after we go through the array, we have to know when to stop. So now we have a while loop. A while loop always has 3 components: the word while itself, a condition that is in parentheses, and also a single statement to specify what do we have to do in a repetitive way. So that is the single statement. Now, in this case, this is a block statement, right? Because it starts with a brace, ends with a closed brace. It is a block statement. So within a block statement, it can be empty. There can be like nothing in between the open and the closed braces. But this time we have 2 statements inside. They're both just assignment statements. So let's go take a look into what is inside the block statement. So inside the block statement, the first statement is an assignment statement, okay? Because when you look at this and the first thing of the statement, it doesn't start with open brace. It does not start with do. It does not start with while. It does not start with if. Well, that leaves us with only one single option, at least up to this point of this class. It has to be an assignment statement because we only have talked about 5 different types of statements. Does that make sense? So I'm going back a little bit in the BNF discussion, okay, from the perspective of the compiler. How does it know, right now, at this point, even not seeing the equal symbol here, how can it possibly tell that it is an assignment statement? It has to do with the types of statements that we have talked about. All right, so as soon as it sees the equal symbol, it goes like, oh, okay, I know this is an assignment statement. We have a left-hand side and then we have a right-hand side. So the right-hand side is everything all the way up to, but excluding the semicolon. The semicolon is a terminator, okay? It terminates an expression, turning it into a statement. So now we look at this and go like, what the, we haven't seen any expressions like that. It is not calculating anything about the sum or addition or subtraction or multiplication and whatnot. Nonetheless, it is an expression, okay? It is also called a condition because any expression that evaluates to either true or false is a condition. Okay, so a condition is a special kind of expression where the value that it returns is not a numerical value, but instead it is returning just the value of true or the value of false. Okay, that makes it a condition. But this condition is not used in the quote unquote normal place because the normal place to put a condition would be right after a while, right after the if. Okay, so those are the only 2 places that we have seen, when we use a condition. So, but there's no rule saying that you cannot use an expression like this, you cannot use a condition as the right-hand side of an assignment statement. Okay, just because we haven't seen it does not mean it is not allowed. Okay, so I'm gonna take a little pause here to talk about learning and also how we put boxes on our head. I'm sure most of you have heard about the phrase of thinking out of the box. Yes, okay, because if you have not, I can do a quick search and illustrate what that phrase means. So are we good with that phrase? Everybody has a general understanding of what it means to quote unquote think out of the box. Okay, so okay, what does it mean? I just want to double check. Okay, okay. Yep. You look for alternatives. You look for ways that, quote unquote, most other people do not consider, right? So that's thinking out of the box. So let me ask you that another question. Who put those damn boxes on our head to begin with? Um, Everything has to do with consciousness, okay? But there are specific ways that we were taught, okay, that put those boxes on in around our thinking mind to begin with. It has to do with repetitive exercises that only show you one or a few ways of doing something, and implicitly, okay, not explicitly, but implicitly, there are no other ways to do this. Okay, am I making that concept clear? Okay. So in order to practice, thinking out of the box, you have to constantly think, is that the only way to do it? Is that a restriction? Is it a stated explicit restriction? Or is it just because, oh, okay, most of the time, when we see examples, that is how we do it, but there's no actual rule saying that you cannot do it in a different way. Are we good so far? So that's a really important mindset. It has nothing to do with algorithm design, but it has everything to do with, when you become a developer, okay, how do you come up with solutions? Okay, is you have to think out of the box. You have to practice. Okay, every time you learn something, you ask yourself, Why is it done this way? Why is the example showing this? Is the example showing me that this is the only way to do something, the only way to use something, or is the example really is just one of the many ways to do something or to use a particular feature? Making that distinction when you're learning a concept is really important. Asking that question, just by asking that question, you are setting yourself to be able to think out of the box. Is that okay? All right. All right. So here we have a condition, but nobody actually says that you cannot have a condition or something that returns true or false as the right-hand side of an assignment. So we go like, okay, let's do it that way. So now we take a look at this expression here and ask, what is it doing? Well, we have so the most important part about reading expressions is to use the operators to tell you the structure of the expression. The ampersand is a conjunction, which is a logical and, okay, which means, okay, if both sides are true, that's the only time the conjunction itself is true. Okay, that's what it means. Okay, that's all you need to do is to evaluate the left-hand side, evaluate the right-hand side, and then do the operation. So now we say, okay, what is on the left-hand side of the logical and? on the on the left hand side of the logical end is sorted itself. Okay, so but for a lot of people who are beginning, who are starting out to program, they go like, but it's the same sorted on the left hand side, this is not going to work. It is going to work, because remember, when you evaluate an assignment, you always evaluate the right hand side first. Okay, whatever that turns out to be, okay, you just go like, okay, whatever is specified on the left hand side, you're going to update it to that value. So that means, oh, okay, this is no different compared to I gets I plus 1. Okay, you can have the right hand side expression evaluate or reference the very same variable on the left-hand side of the assignment. It is not a problem at all. Okay, what about the right-hand side? Okay, so when you look at the right-hand side of the conjunction, you see something that normally only go into the condition of a conditional statement or the condition of a while and so on and so forth. Well, guess what? What does the ampersand expect on the left-hand side, on the right-hand side? Both sides need to give you something that's either true or false, right? It doesn't make sense when you say 2.5 and 6. That really does not make sense, okay? From the perspective of an operator. So in this case, the only restriction is whatever is highlighted here has to give us an answer of true or false. Okay, fine. So what is that? The operator in this case is called a relational operator, but you don't really need to know that formal name. It's called a relational operator because it relates the left-hand side to the right-hand side, whether the left-hand side is less than or equal to the right-hand side. That's basically what it is. So what are we comparing in this case? We're comparing a particular element, I, of array A, to another element of A, which is at the index of I plus 1, the one that is right next to it. That's all we're doing, okay? And we're asking, is the one, is a bracket I less than or equal to a bracket I plus 1? Because if it is the case, then the array is still sorted up to this point. Now, I don't know what is after, okay? But up to this point, I can say, yeah, if it was sorted already before, we are confirming that, yep, including this new element that we're looking at, it is still sorted. So we are basically keeping track of a quote unquote running window of whether the array is sorted or not. We just extend that window one element at a time as we go through each iteration of the loop. Is that okay? So once we have that confirmation or not, okay, because it might be that this is not the case and sorted becomes false, that's okay. We'll deal with that later. Okay. Then we say I gets I plus 1, which means, oh, let's get ready for the next item that we need to compare. So it keeps doing this until this condition is false, until this conjunction becomes false. Now, how can this conjunction become false? Well, since it's an and, that means if at least one side is false, the whole thing is false. So now we think about what does it mean when sorted is false? So now you have to think about how can sorted possibly become false? Okay, so let's think about that for a moment. It was initialized to true, right? I don't see anything here that explicitly says, oh, sorted is now false. Okay, we plug in sorted being true here, and we go like, okay, so under normal circumstances, okay, sorted and blah blah blah, and sorted is already true to begin with. So the only thing that can make sorted become false is going to be the right hand side of the right hand side on line 4. This is the only thing that can possibly make sorted to become false. Yes, yes. But this is the only way, okay? The highlighted condition being false is the only reason why sorted as a variable can store a value of false. Are we okay with that analysis? Okay. But but what does it mean when the highlighted condition is false? It means a bracket I is greater than a bracket I plus 1, which means according to the way we define what it means for an array to be sorted in a non-decreasing way, if the highlighted condition is false, it means guess what? This array is not sorted. Does it make sense? Because if it is false, it means we just found a particular element of the array where it is greater than the one that is following it, which violates the rule of what it means to be sorted in a non-decreasing manner. Are we good so far with that analysis? Yes? You have some question. Go ahead. The rule that we talked about earlier, so I'm going to use the mouse to just kind of go back to the rule itself. So we are talking about this rule here. Okay, to be sorted in a non-decreasing order means we have to satisfy this requirement. But when this condition is false, it it means only one thing. It means a bracket I for some kind of I is greater than a bracket I plus 1, which means somewhere along this long chain of less than or equal to, we broke that chain somewhere. Hmm? Because the highlighted expression evaluates to false. We, I will illustrate this with a trace, with an example. Yep. But it is important to kind of read the algorithm itself first to understand, okay, so just approximately, okay, roughly, how does it work? And then we go through the trace to confirm, oh, okay, this is exactly how I thought it would work. Okay, so another moment, okay, I'm pausing here. Another moment of talking about, just how the learning process itself. There are usually two ways of learning, and most people kind of do a mixture of the two. One type of learning goes by the rules, okay? Tell me all the rules, okay? And I will try my best to understand the rules in its abstract way. And then I would use an example, which in this class will come in the form of a trace, to confirm my understanding is correct. Okay, in other words, I would understand what exactly is a loop, what does it mean to be sorted. I would understand this code here, okay, like the way that I have been analyzing it, for maybe another, 20 minutes or so, and then I would go like, okay, I think I got it. But how can I confirm that I really understand the past 20 minutes, right? I go for a trace. Okay, so I go for a trace just so that I can illustrate to myself that I can follow the rules. I understand how this algorithm is supposed to work, and it works the way that I expected. That's one way of learning. That's actually my way of learning for the most part. Okay, I use this method of learning. The other way of learning is to say, okay, I vaguely understand what this is about, okay, but I'm going to use examples to help me understand exactly what it means. In other words, you look at examples of arrays that are sorted, you look at examples where arrays are not sorted, and then you look at the traces, okay? You do this like 6 or 7 times, okay? And then your brain starts to notice the pattern. In other words, you're extracting a pattern from examples of running the algorithm, and that abstraction is how some people learn. Okay, so do we understand the two ways of learning at this point? I can present this in a more painful way. Yes, there's always a more painful way, and I always find it. Okay, so the more painful way to look at this is to say, tell a young child, okay, don't touch that cup. It contains hot water, and it's gonna burn your finger. Okay, not burn as in the blister kind of burn, but you will feel that pain. Okay, okay, so one child, okay, me, would look at this and go like, okay, I get it. Okay, hot means pain, and do not touch the cup when it's hot. Okay, so um, I might ask my younger brother to touch that cup just to confirm the theory, okay? And go like, and see him go like, ow, why would you ask me to touch that cup? Just to confirm a theory, that's all. I'm sorry. Okay, that's one way of learning, okay, is to learn the rules, then confirm your understanding by running an experiment. The other way of learning is somebody tells me, oh, this cup is hot, okay, has hot liquid in it, don't touch it. And I go like, okay, touch, ow, that's hot, okay, and then wait a little bit longer and go like, hmm, still not convinced. Do it again, touch, ow, it is still hurting. Then start to sink in. It's like, oh, okay. When somebody says hot is painful, I have now confirmed that by experiments. So now from here on, I learned that hot means pain. Okay, so next time when someone comes up with a like a some meat from a barbecue and they go like, "Oh, this is still hot. Don't touch it." Then I understand and go like, "Yeah, hot means bad because I remember my experience of touching a hot cup and that burned me." Okay? So that's the second way of learning. Okay? Now there's no right way or wrong way of learning, okay? But I can point out the second way of learning is not particularly helpful in computer science because when people learn by examples and then they do abstraction and then they generalize, there is always a chance that their generalization is missing some of the nuance of the concept that they're trying to learn. Okay, so that means you can have a lot of examples to illustrate a particular concept, except the examples did not cover one of the more important and nuanced way of running an algorithm or demonstrating a concept, and then that will never be learned because you never made that observation. You could never have incorporated that concept into your framework of understanding because you never saw a single example to illustrate that point. But if you learn by the rules, then you know that rule has always been there, even when there were no examples to illustrate it. So I'm not sure whether this is going in the direction that I want this discussion to go, but I think it is something that you can probably kind of keep in your mind and then continue to kind of ask questions about that. Okay, because if you change the way you learn, okay, early on, it changes your entire trajectory throughout college and your professional life. So I just kind of want to make that point because I think it is important. All right, so getting back to this example. Okay, so this is the only part that can make sorted false. So that means if this, if I evaluate this conjunction and the left-hand side turns out to be false, so that means, oh, okay, so at least I found one instance where a bracket I for some value of I being greater than a bracket I plus 1, because that's the only way for sorted to become false, which also means I have no reason to continue this loop anymore. Because in order for an array not to be sorted the way that we want it, you just have to find one particular chain, or find one particular link in the chain where the rule was broken. And that became not sorted anymore. Is that concept understood okay? I'll give you some concrete examples. Okay, so hopefully my tablet is behaving today. So let me double check. Yep, it's on the correct router. And this one is on the correct router as well. Okay, this is good. Okay, so we can now take a look at an example. Okay, and everything is still getting recorded. So if you want to record, if you want to write it down, it's good. If you want to just kind of jot down the time, that works too. So if I say, okay, I want sorted, okay, means non-decreasing. Okay, so this is decreasing. So I'll give you two arrays. Okay, I give you the values of 23, 64, 100, and 209. Okay, are these four numbers sorted in the way that we want? Non-decreasing. Non-decreasing, not decreasing. Yeah, yeah, so this is cool. Okay, what about this one? It's like, what is this sorted? 0, 0, 0, 0, because they're non-decreasing, right? Okay, non-decreasing means they can all be the same. Okay, so now let me go like 1, 0, 23, 22, and then a 107. Is that sorted? It is not sorted because, hey, look at these two. This is in the wrong order. You only need one instance like this within the entire sequence that is breaking the rule, and then you say, oh, okay, this entire sequence is not sorted because somewhere in the sequence the rule was not followed. Yep. Well, we need an algorithm to find this. The one that we are talking about will be able to detect exactly this and go like, hey, this array is not sorted. Do I really need to look at 107 once I have looked at these two? Nope, because this is enough reason for me to go like, okay, we got an answer already. Okay, this array is not sorted. Let's get out of here. Not, because there's no reason to continue. All right, so that goes back to the algorithm itself, and it also kind of goes back to the discussion that we already had regarding lazy evaluation or short circuit evaluation, which is basically saying if sorted is false, don't bother to even go compare I to n minus 1 because we're just going to get out of the loop anyway. I don't really need to know whether I is still less than n minus 1. We can just exit. Okay? Yep. In the trace. Yep, that is correct. So in the trace, we emphasize that we are short circuiting by just saying sorted equals false or sorted is false without the conjunction and the other side because we don't need that. Yep, so that is a very good point. Thank you for pointing that out. All right, but what if sorted is still true? In other words, either we just got into the loop the first time, or in all the past iterations of the loop, this condition on line 4, let me highlight the condition first. So, or this condition is true for all the previous iterations. Then we go like, well, I really prefer to have this algorithm or this loop finished. But if I is less than n minus 1, that means I have at least one more pair of elements in the array to compare before I can confirm the entire array is sorted. Okay, when this condition is true, it means we have not reached the end of the array. We are only confirming things like one by one, but we haven't really reached the end. So if this condition is true and this condition is true, together, okay, what do they mean together? Let me just kind of highlight the entire thing. So when this entire conjunction is true, it means we everything I have seen up to this point of this array is sorted, but I'm not done yet. There are still additional items in the array that might show that the array is not sorted. So we have to continue the loop. We have more iterations to perform. Is that okay? All right. So, so what I have just talked about, which is a dissection of the meaning of all of these statements here, it is important. Okay. So you don't have to be taking notes because I know it's kind of difficult to take notes when I'm talking. But when you have time to go back to revisit this topic, you might want to jot down some notes, okay, of the process of how I analyzed this algorithm. Okay, in other words, semantically speaking, semantically means in terms of the meaning, of the code here, how the different expressions relate to each other. Okay, that is a very important step to do if you want to be able to come up with your own algorithm in CISP 360. So in this class, CISP 300, I'll be the one making all the algorithms, but I'll explain how the algorithms work, how the different parts of the same algorithm relate to each other, in CISP 360 and beyond that, you'll be constructing your own algorithms. So having an understanding of how different parts of the same algorithm work together is important. Okay, so that's kind of the focus. This would definitely be one of the ways you can use the 2 additional hours for each hour that you're in a lecture. Okay, are we good so far with that? All right, cool. All right, so I think we have talked about enough about analyzing the algorithm, and by understanding the control structures, by understanding what arrays are, what we can do with arrays, and also the nature of conjunction, and here and also here, I think we are ready to take a look at a few examples. In fact, we're going to take a look at the examples that we were just talking about. Okay, we'll pick 3 of the representative ones. So these are the 3 ones that are representative. That's what we're going to do today. So let me close the tabs that we don't need anymore. Okay. And then we make a new Google Sheet for today. And that's always going to be in today's date. So it's easy for you to find. Okay, so you have the video, you have the spreadsheet that serves as a log of what we talk about today. Today is the 29th. Just wanted to make sure. There we go. And then the algorithm is already in the module, so I'm just going to do the usual trick, which is taking a screenshot of the algorithm itself, put it to the upper right corner, so I don't have to kind of copy and paste this again into the spreadsheet. Okay, so we put it, stash it all the way here, and make it always on top. Okay, so this way we can see it while the spreadsheet, while the browser is on the spreadsheet itself. All right, so this is sheet number 1. So let's go ahead and set up all the columns. So we got line number, we got I, we got N, and then we have the array itself. So this time the array has 4 elements, and we always start with element 0. That's one of the rules related to how we use arrays. So this is going to be how we set up all the different columns, and we're going to get rid of this portion here so we can, so it doesn't get in the way. All right, so most of these columns can be a little bit narrower. Okay, so I'm going to say all of these can be narrow like that. Comments, it's always going to be a little bit longer. Line number can still be a little bit narrow, like so. All right, so I think we have set up everything. All right, so we always think about the precondition. In other words, what are we given with? Okay, what do we know before the algorithm starts execution on line 1? It doesn't matter what I has, so we just say that I can be unknown. It doesn't really matter. N needs to be known. Okay, so in this case, we have N being 4 because N is telling us the number of elements in the array. Now, is that always the case? In other words, is the variable name N special? The answer is no. Okay, it is just a convention that I use, in this class. I always use N consistently to indicate the number of elements in an array. Okay, but it doesn't have to be N. You can name it length. Okay, length of array A or A length or something like that. Okay, it's fine. So I'm looking at my first example, which is 23, 64, 100, and 209. That was one of the examples on the tablet. Okay, so that is the initial condition, and I'm missing one more variable, which is sorted itself. So sorted, even though it is storing a kind of funky value, which is Boolean and not a number, it is still a variable. So as such, it also needs its own column. So we'll just say this is sorted. It is its own column. And because the first thing we do, or the second thing we do, is to overwrite the value of sorted with a constant. So that means whatever value it starts off with is also not important. And therefore, it starts with an unknown value. Yes. I'm not sure. There are only four elements in this array because I was trying to reproduce a test case that we were talking about earlier. So that's the reason, right? Because I was referring to the first test case here. Yep. So does that explain why there are only four elements and also why the elements are pre-initialized to exactly those values? Because I was just trying to illustrate that one example. Okay. All right. So are we good? Are we ready to look into the trace itself? Okay. So at this point, okay, depending on how you learn, but the way that I learn is by this point, I think I'm just looking for verification that my understanding of the algorithm, my understanding of everything about the algorithm, and my understanding of what is sorted is correct. I'm looking for a verification, not so much to use the example as a way to generalize or to abstract. It's just a way for me to go like, hey, Luke, not Luke, my brother is Felix. Hey, Felix, go touch that cup and then watch his expression. Okay, this is me telling my brother to touch the hot cup and watch his expression. Okay, all right, so let's go ahead and start with this. So we have line one, I gets initialized to 0. Line two, sorted becomes false. Okay, and false is always uppercase in the spreadsheet because it also has a special meaning in the spreadsheet, which is okay. Either way is fine, right? So we go to line three. So on line three, we have to evaluate the conjunction. So the first thing we evaluate is sorted. Well, I said one thing and I do the other thing. This is actually supposed to be true. That was my bad, sorry. So in this case, sorted is true, which means only knowing that sorted is true does not mean I know, what the conjunction is going to return because now it depends on the right-hand side. So that means, okay, we cannot do the short circuit thing. So now we have to say, okay, tell me what about the other side. I has a value of 0. We're comparing that to n minus 1. N is 4. 4 minus 1 is a 3. So the question is really asking, is 0 less than 3? Okay. Okay. So because it is true and true, the whole thing is true. All right. So now we go to line 4. All right. So line 4 is kind of interesting because now we have to evaluate the right-hand side of the assignment, which is this expression here. So the first thing we say is, oh, it's a conjunction. And the left-hand side of the conjunction is sorted. Well, sorted is still true, okay? So that means I cannot determine the value of this conjunction just knowing that sorted is true. Now we have no choice but to evaluate the right-hand side. So now we evaluate the right-hand side of the conjunction on line 4, which is saying, okay, give me the value of A bracket I. Okay, so this is going back to array indexing that we talked about in the previous class. So can someone tell me which column I should be looking at when I'm trying to evaluate the value of a bracket I? Yep, column E, because I has a value of 0. So the expression I gives me the value of 0. And then I just go like, oh, okay, so you're really just looking for a bracket 0, which is our column E. So that means I'm comparing the value of column E versus the value of column F, which also means I'm really just comparing 23 and 64 and see if 23 is less than or equal to 64. The answer is yep, it is true. So that means we have true, and that means this conjunction returns a value of true, and we store the value of true back into sorted. So we say, yep, sorted is in fact updated to the same value that it had already from before. So this is also an important thing to kind of remember is in this class, in the context of this class, even if the value that you are putting into a variable is the same as what we had, you still have to update the corresponding cell. Okay, because this is the only way I can tell whether you know about the actual update of the variable, even though the update is updating to exactly the same value that it had before. Are we good so far with that? Okay, all right. So after line 4, we get into line 5. I gets I plus 1, so I becomes 1. Then we go back to the beginning on line 3 to reevaluate the condition. So sorted at this point is still true, which means I need to know evaluate the second part. I has a value of 1, n minus 1 is a 3, 1 is less than 3 is true, true and true is still true. So now we go for the second iteration. We get to line 4, okay? So line 4, this is the expressive power of array indexing because line 4 looked exactly the same. Okay, if you go to the trace itself, row 6 versus row 9, they are both representing what happens when we execute line 4, but at different times. Okay, so it's the same line. We're still evaluating the same thing, but because I has changed, okay, the value of variable I has changed. So that means a bracket I is no longer referring to a bracket 0 because I now has a value of 1. That's right. And then 1 plus 1 or I plus 1 is now a 2. So we are really comparing column F versus column G, okay? So this time we're comparing 64 against 100. Well, guess what? 64 is less than or equal to 100, right? So that means we still have true, and then we store true again back into variable sorted. We go to line 5, increment I to 2, go back to line 3. So line 3 is evaluating sorted. It is true. Then we evaluate I is less than n minus 1. I has a value of 2. N minus 1 is 3. 2 is less than 3 is also true. So that means the conjunction itself is true. So now we go like, okay, more work to do. Go back to line 4. Okay, so you probably already know. Oh, okay, this time we're comparing column G to column H. We're comparing 100, which is the value, to 209, and 100 is less than or equal to 209. So that means once again, we have true and true on line 4 right here because sorted itself is true. And then we just said how a bracket I is less than or equal to a bracket I plus 1 is also true. So now we store true again in sorted. We go to line 5, finally increasing I to 3. Go back to line 3. And now we say, is it sorted? Is sorted still true? Yes, it is. Then you have to go look at the second one, which is I, which is now 3, less than n minus 1, which is also 3. Nope, 3 is not less than 3. So now we have true and false, right? Because the second part, the right-hand side is false. So we have true and false, which is false. Okay, so the whole thing is false. But that means, oh, okay, we are done. We can now go to post, and we have the conclusion. Okay, the conclusion is the variable named sorted is telling us the conclusion. The array is, in fact, sorted. Are we good so far? So this is a it's a simple algorithm from a few perspectives. It's relatively short, only has 6 lines. Other than the array, we really only have two variables. Okay, when you look at how which variables got changed over time, it's really just sorted, which it got the same value over and over again, and also just variable I. Everything else stayed pretty much the same, or I shouldn't say pretty much, they say exactly the same. So from that perspective, the algorithm is relatively simple. But would I call it a simple algorithm, especially in the context of CISP 300? I would not, because it involves a lot of things that takes a lot of analysis to figure out how they connect. In other words, there's a variable sorted, but how is it really used in the loop as a condition, as a part of the condition? That is not simple, okay? It is complicated in a certain way. And then we also have the way of updating sorted, okay, which is this expression here. What does it really mean? Okay, why do we use a conjunction instead of a disjunction? Okay, so all of those are questions that make this algorithm actually not as simple as it seems. We also got exposed to the concept, well, a few concepts that are quote unquote new, but they are not. Okay, we got exposed to the concept that sorted is a variable, but instead of storing integers, it is now storing a Boolean value, true or false. Okay, that's not a new concept. Okay, assignment is still assignment. Okay, except, oh, okay, so there's no actual restriction per se of what we can store in the variable. Okay, so at some point we're going to talk about types and so on and so forth, where we'll start to put a few restrictions on these things. But for now, we just go like, oh, okay, so variables can store all kinds of values, including Boolean stuff like true, false, in addition to numbers like 0, 1, 2, and 3. So from that perspective, this algorithm is actually kind of complicated, okay? But it's only complicated if you try to look into it and try to reason out why it works, okay? Now, there are two separate questions. They are related. To many people, they are kind of the same thing, but they are really distinct. One question is, okay, there are three questions, okay? There are the why, the what, and then the how. Okay, so those are three different questions. The first question is, why do we even need an algorithm like this? Why do we need to know whether an array is sorted or not? Well, the answer is if an array is sorted, we can apply much more efficient, much more efficient algorithms to confirm whether something is in it or not. Okay, so from that perspective, we have reasons to try to determine whether an array is sorted or not. Because if it's not sorted, then we have to go the slow way. There are no other ways to get around it. But if it is already sorted, we can use this really crazy efficient algorithm called binary search. So that's the why. The second one is the what. Okay, what is this algorithm? So I would say the what is really the trace itself. Okay, in other words, the trace shows you when you run the algorithm, what's happening. Okay, the how is the analysis that we talked about earlier, which is making all the connections between all of these various components of the algorithm. That explains how the algorithm works the way that it does. So those are three different questions. They are all important when you're learning something, okay? So let me ask you another question because these are all kind of reflective questions that only you can answer, but I have a general idea of what the answer is supposed to be, but I will let you figure it out. Throughout high school and many other classes that you take, even at the college level, which of the three questions do they focus the most on? The why, the what, or the how? One explains why this topic is even important. One explains, okay, this is the concept of taking the derivative of a power of x, okay, and and this is the way, this is mechanically the way you do it. And the third one is how, okay, which is so how does this work, okay? Y is dx squared, over dx is 2x, okay? So instead of memorizing the pattern, you're trying to understand, oh, okay, so that's how it's derived, okay? This is why, this is the way it works, okay? So which one do you think your classes focus on the most? The why, the what, or the how? It would be the what. How to make use of something mechanically. Okay, so in a calculus, okay, maybe you have not started to take calculus classes, algebra. Okay, so in algebra class, okay, you have to do a lot of exercise, right? So every single exercise goes like this is the, this thing is supposed to equal that thing, so derive and show me why they equal to each other. So you're exercising a lot of the rules, right? Your commutative, distributive, and blah blah blah, and so on, right? So you're mechanically going like, okay, I can I can do this mechanically, but why does it work? Well, they don't really explain that, right? And they don't also always explain why algebra is actually important in the first place. Are we getting the point? The differentiation between the what versus the how. Okay. So why is that important when you're learning something, especially in your major? I'm assuming that you guys are all going to be computer science or computer engineering or electrical engineering majors. That's your plan, right? Okay. So why do you think asking these three questions are important? And also why just understanding the what is not enough? The why gives you an idea of when this becomes useful. Okay, under what circumstances do we apply what we are learning here? Okay, because otherwise it's just some knowledge in your notebook, right? It's just a few pages of your notebook, or a few pages in your textbook that you don't have to touch ever again after this class. So the why helps you connect things that you have learned already in order to recognize, oh, I can use what I learned in that class now. And that could be 6 years, 10 years down the road. That is the importance of the why. Okay. The what, we kind of know why it is important because you want to pass this class. So that you can move on to the next one. What about the how? What about that whole analysis of, let me tell you why this algorithm works? Not why this algorithm is important, but why it works. What is the importance of answering that question? Tech, you just gave us the algorithm. I know how to follow it. Isn't that enough? Well, if I give you the algorithm in CISP 300, the AI know about this algorithm already. So does Wikipedia. Okay, so knowing the algorithm in the sense of I know how it is spelled out, I know how to trace it, that part is not important in the long run. In the short run, yes, if we want to pass this class, that's kind of what is important, okay? But what about in your future, like 6 years down the road? Why do you think I focus also on why the algorithm works? Hmm. You, yep, exactly. So you need to be able to come up with this algorithm, even though it's easy to search, right? You just go to Wikipedia and go like, give me an algorithm that can confirm whether an array is sorted or not. Bam. Okay, done. Okay, but the mentality is if you don't apply that principle, okay, of trying to figure out why this algorithm works in the first place, when it is simple like this in CISP 300, you are not developing your mental, your cognitive muscles to deal with the problems that you need to solve. And those problems are one, important enough, and two, difficult enough that people would actually pay you to get it done. Am I making that point clear? Okay. So by developing those cognitive muscles, okay, think Arnold Schwarzenegger, but not in a physical way, okay? So by practicing this early on, you're developing that mentality. You're developing all those muscles. So by the time you graduate, by the time you get into a job, by the time you get to mid-level as a software engineer, you have all the resources that you need. It is all in you already. Is that okay? All right. So I think this is an important discussion. I know most people are going like, this is this is not programming, man. It doesn't really, it's not even important. Okay. Do I need to know all this crap to pass this class? The answer is no. You do not need to know all that stuff to pass this class. Okay. All you need to do is to go like, if the algorithm looks like this is what the trace looks like, and I know how to mechanically do it. That is all you need to pass this class with a good grade. Okay. But that is not enough in the long run to be successful. And I want you to be successful. I don't want to sound like I'm your dad, but so line 4 or row 4. So we have row numbers here to indicate row 9. This one? Okay. So row 9 is evaluating. So, okay. So the first thing we want to know when you look at a row is what not line number we are referring to. We are referring to line 4. So that means this is the result of executing line 4 because it is an assignment statement. We somehow figure out that true is the value of the right hand side of the equal, and then we store that into the variable named on the left hand side of the equal, which is sorted. So that's the most immediate way to explain it. But then what you're really asking is why the right hand side of the equal evaluates to true. Okay, that's what you're really asking. So to answer that question, we look at the right hand side and we say, what was the last thing that we do on the right hand side of the assignment on line 4? It's the conjunction that I'm pointing at right now. Okay, so now the question is, why is it returning a true? So you look up the truth table of a conjunction, you go like, oh, so the only time a conjunction returns a value of true is when both sides are true. Okay, so now you look for that, right? You look for confirmation that both sides are true. The left-hand side, which is just the value of the variable sorted itself, is pretty clear because it had the value of true to begin with. So we know the left-hand side of the conjunction is already true. Okay. The right-hand side is the one that is kind of funky because it's like, ugh, it's a comparison of some kind and it's appearing inside the right-hand side of an assignment. But it's okay. Where it appears does not really matter. We just have to know why it is true. So the right-hand side of the conjunction is basically a comparison, confirming or not a less than or equal to. So what are we comparing? We're comparing a bracket I. At this point in time, okay, variable I had a value of 1. So that means this a bracket I here is evaluating a bracket 1, which according to our table here is referring to column F, which has a value of 64. And likewise, a bracket I plus 1 is evaluating a bracket 2, which has a value of 100. So now we are really comparing. This is now really just 64. This is really just 100. 64 is less than or equal to 100 is true. So that means the less than or equal to as an operator is returning a value of true, which is then utilized as the right-hand side of this conjunction. So by that time, we already know that the left-hand side is true, the right-hand side is true too. So looking up the truth table, true and true is also true. So this conjunction here is now returning a value of true, which is then stored to the variable sorted. And that's why we recorded true on row 9 as the update to variable sorted. So does that answer the question? Okay. And don't ask me to repeat that because I cannot remember what I just said. But everything is being recorded. That's the whole thing about being recording everything so that you don't have to write it down. You focus on understanding what I'm saying, and then you focus on formulating your question to ask in the class. Okay. Now, I don't know how other your professors teach classes. Okay, and that's none of my business. Okay, but from your perspective, you want to be able, okay, to focus on what the professor said, try to understand what the professor is saying, make sure you understand it. And if you don't, okay, you know, have the opportunity to ask questions. Okay. If the professor is busy writing more stuff on the whiteboard or trying to erase something, you can always raise your hand and go like, I'm not done. Can we stay on this for a little bit longer, or I need a little bit more time to formulate my question. Can I do that? Okay, because it is important. That is one huge difference, at least in my mind, between a class that is done completely online, 100%, an asynchronous, versus a face-to-face class like this. Okay, it is the ability to ask questions in real time. I really, frankly, do not know how to teach a class online. Okay, what does it mean to have a lecture when it is completely online? What is a lecture? Okay, am I lecturing you? In a way, yes. Okay, but it is not a one-way thing. I keep asking you guys questions, right? I keep asking, okay, what is your opinion on this? Okay, what do you think of this, and so on. And you always have the opportunity to ask questions too. I mean, many of you did. Okay, you raise your hand, you ask questions. That to me is what a lecture is supposed to be. And I cannot do this online, especially not when it is asynchronous. So, any other questions? Nope. So I'm saying all of this also to give you more information to make decisions in your later semesters. Okay. In other words, if a class is offered in person and also at the same time, online by different professors, maybe the same, maybe over different colleges. So how do you decide whether to take a class online versus taking it in person? I'm trying to give you more information as to, how to make that decision. What do you evaluate when you try to make that decision? I can totally understand why people want to take classes online. It is flexible, right? Okay. And it does not give you, it doesn't create time conflict with your other classes that must be taken in person, right? Because you won't run into a situation of, man, this class is overlapping with that other class that I also need to take. No, if one of them is completely online and asynchronous, there's no restriction. Okay, you can always go like, okay, when I have time, I can study for this class, and then this class is in person only, so I can make my schedule a little bit more flexibly. So I understand that part. But at the same time, if a class is in your major, like this class, CISP 360, 400, 430, 440, 310, okay, it means you probably want to understand as much as you possibly can in those classes, not to only get a good grade so that you can transfer to wherever you want to transfer to, but also to make sure that after you transfer, you don't feel like I have no idea what this professor is saying. Okay? That is one of the scenarios that I really do not want to happen. Is after people transfer, then they suddenly realize they're not ready for that transfer. Because after you transfer, how much do you pay for each semester? Is it going to be like $42 per unit times maybe 15 or I mean, I know crazy people who take 20 units per semester. So 20 times 42 is still what? $840, right? How much does it cost people per semester at a CSU or UC? 20K, well, not per semester. That's probably including lodging, like, dorms and whatnot. I think the tuition itself is around 10, 15, 10 to 13, depending on whether it's a UC or a CSU, but it'll be in the order of $10,000. And that's only if you are not living on campus or needing to rent an apartment. And that's on a per semester basis. And with a UC, it will be on a per quarter basis, which means you have to pay 3 times a year as opposed to two. Nope, it does not. Okay, so as long as you're enrolled, you still have to pay that number. Okay, we can look it up. Uh, how, okay, what is the per quarter tuition of, we'll just pick UC Davis. All right, so it's only 5,000 something dollars. Okay, so but per year, okay, it will be $17,000, and then plus dorm. Dorm is actually expensive. Okay, dorm is probably around 1,000 per month to 14-ish hundred, depending on which the area. So basically, it's good to figure out things before you transfer. I'm just gonna put it that way. Yes. Okay. All right. So we're gonna move on. Okay. We will continue with the trace, and this time we're gonna start with a different trace. But before we move, do we have any questions? I apologize for all the digression, but getting back to the algorithm, do we have any questions before we move on to another trace that works on a different array? No questions? Okay, all right. So we're going to copy some of the formatting of this and then put it into the next one. Okay, so I'm going to copy this thing and copy that to the second trace here. So I think, just because of the time that we have, I'm going to move on to, all right. I'm going to move on to the case where the array is not sorted, which is the last one. So we have 0, 23, 22, and 107. So that's what we'll do. So we have 0, 23, 0, 23, 22. Oops, nope, that's not the one. This is still 4. We have 0, 23, 22, 107. And then we'll restart the entire trace like so. Okay. So we are still starting with line 1, still doing the same thing. I gets initialized to 0. Line 2, sorted becomes true. Line 3, sorted itself is true. I is 0. N minus 1 is 3. 0 is less than 3 is true. So we have true and true. So that means I just have to write the entire thing. Sorted and I is less than n minus 1 is true. Get to line 4. All right, so the first time we get to line 4, I is 0. So we are essentially just comparing a bracket 0 against a bracket 1. And we're comparing the values of 0 versus 23. 0 is less than or equal to 23. That is true. So once again, we have true and true. So that means we update sorted with the value of true. We get to line 5. I becomes 1. We go back to line 3. Sorted is true. And then I is 1. N minus 1 is 3. 1 is less than 3 is also true. We have true and true, which is true. So this is the magical moment. We get to line 4. So this time, when we get to line 4, the left-hand side of the conjunction on line 4 is still true. Okay, that part is pretty much the same every time we get to line 4, because otherwise we would not be on line 4. Okay, we cannot possibly be on line 4 if sorted is not true to begin with. Okay, so the key is really the right-hand side of this conjunction here. I is now 1, so we are comparing a bracket 1, which has a value of 23, against a bracket I plus 1, which is a bracket 2, which has a value of 22. 23 is less than or equal to 22 is false. So that means we have true and false. Looking up the truth table, that means the conjunction is false. So now we go like, oh, okay, it is a false. We still go to line 5, okay? Because line 5 is right after line 4. We always go to line 5 after line 4. I gets incremented 2, and now we go back to line 3. This time, when we get back to line 3, the left-hand side of the conjunction, which is really just sorted itself, is already false because we just updated the value of sorted to be false. So that means with this conjunction, only the left-hand side is needed to conclude the value of the operator itself, which is false. So now we can just say sorted is false, and we can exit the loop right away and go to post. So we come to the conclusion that the array is not sorted because sorted is false, not having to go through the same number of iterations as before. So is that okay? All right. And we only have about 4 minutes left here, which I'm going to kind of go back to what I talked about in how to learn just a little bit. If a professor only gives you cases where the answer always come up to be true in sorted, then you would not be exposed to examples when the array is not sorted, which means for people who learn from examples to learn by examples, they would not have a more concrete learning in that experience. But if you learn by the rules and you only use examples to confirm your understanding, then you'll still be on better or more solid ground. And also if you learn that way, you would be able to come up with your own test case. It's like, okay, professor, all your examples are ending with sorted being true. Let me think of a way so that sorted becomes false somewhere within the algorithm. That exercise alone is helping you to develop your quote unquote the cognitive muscles that will be very helpful later on in your classes and also in your career. So I just kind of I want to reconnect to those concepts that we talked about earlier in today's class because I think that really is important. Especially the earlier the class is, the more important it is to talk about those concepts because you have a longer trajectory to actually make use of the concept of how to learn. Learning how to learn is more important when you're at the earlier part of the trajectory. All right, well, that's all I need to say for today's lecture. Once again, it is optional, but I thank you for being here, and I'll see you all on Wednesday for exam one. So don't forget the exam is on Wednesday, but it does not include anything with arrays. Okay, it is everything before arrays. All right, cool. Let me stop the recorder, get it uploaded, and I need to go back to my office to get something. So